So let's discuss a problem from classical mechanics, and it comes under the topic Newtonian mechanics and rigid body dynamics. So here is the problem. So a particle slides on the surface of a fixed sphere from the topmost point. The angle at which the particle leaves contact with the sphere is. So here what they are saying is, so we need to imagine a diagram according to the question. So this is the diagram we could imagine. So a particle slides on the surface of a fixed sphere. So this is a fixed sphere. This largest circle. So this large circle. This is a small circle. So this is the sphere. Slides on the surface of a sphere from the topmost point, and particle is this small circle. The angle at which the particle leaves the contact with the sphere. So in this, what we have to find out is the angle at which this particle leaves contact with this circle. So this particle would have started from here. So it would have slided from here, slowly it might have slided, and finally it might have reached here, and finally it would lose contact with this sphere, and it would fall down because of gravitational force of attraction. So in this question, what we have to find out is angle at which the particle leaves the contact with the sphere. So it goes on sliding because of gravitational pull, and finally it must fall down. So we have to imagine just like there is a large ball. So upon this large ball, we have placed another small particle or another small ball. So what would happen? It would slide down immediately because of gravitational force of attraction. It would be acting on this ball. So here in this question, what we have to find is the angle at which this particle would lose contact with the sphere. So let it be this angle. So this is the sphere. So here is the normal. So initially the particle started from here. It slided down. Finally it lost contact over here. So this is the angle this is the point at which the particle lost contact with the sphere, and this is the angle from here to here. This is the angle. So we need to find out this angle. So for this, what we have to do is let it slide through an angle theta. So let us imagine that let that angle be theta, the angle at which this particle would lose contact from the sphere. The speed at this position can be easily found using energy conservation principle. So at this point, the speed of the particle could be found by using conservation. So it would be sliding. It would have some sort of speed. It would have gained. It would not be at rest, and finally it would leave. So we have to. So that speed could be found from this energy conservation principle. So here we need to apply energy conservation at this point and energy conservation at this point. So here initially the particle was here. So initially it was at rest position. It would be the speed of that particle would be 0. So it would be having only potential energy but no kinetic energy. So we know formula for potential energy, that is mgh. So mgh. So here we need to find height. So here actually half of the sphere, if the particle is moving on the top of the sphere, immediately it would face gravity and it would fall down, and remaining half would be, however, would surrender to gravity. So here we need to take the height from this center of mass point, from this reference point, because below half of the sphere would actually face surrender to gravity, and this part. So when the particle is moving on this top, and by the time it reaches here, it would fall down eventually. However, the particle is not going to move on this bottom part of the sphere like this. It would lose contact. So if you want to make the particle to move without contact, means forcefully we have to catch it and we have to make it move. So however, it would lose contact on the upper half of the sphere itself. So here we have to take this as the reference point. So from this point to this point height, so this is the center of mass point, so this is the reference point. So how the at this point the potential energy would be 0, and at this point the potential energy would be mgh, that is the radius of the sphere, that is nothing but mgr. So here to here, that is nothing, height is nothing but radius of the sphere, large sphere, so mgh. So as we are taking, this has the reference point. So at this point, when the particle is at this point, it would be having only potential energy, so mgr, and no kinetic energy. And the particle has moved from here to here. So from the law of conservation of energy, we have energy of the particle at this position is equal to energy of the particle at this position. So then at this position we need to find out the kinetic energy and the height of the particle. So from the diagram we are having, this is the R diagram. Here this is the sphere and this is the particle, and force acting on the particle is gravitational force. So it would be acting vertically downwards. Gravitational force would always act vertically down. So this is in vertical position, so vertically downwards for the particle. So if the particle was here, it would have act vertically downwards, so like that. So and as this particle is in contact with this sphere, so it would have contact force, that is normal force. So just like, so if this is a table, if there is a book placed over this table, so what are all the forces acting on this book is gravitational force, which pulls the book downwards. So then the book should move down, it should break down the table wood and it should fall down, but it is not falling. Why? Means because of opposite force, contact force, that is normal force. So this normal force is a contact force, means this force would act only when the bodies are in contact. So when the bodies are not in contact, it would not act. So this book, as this book is in contact with this table, so gravitational force would be acting downwards and contact force would act in opposite direction, upwards. So hence both the forces would get balanced in this case. Hence the book would stay in that position. And here, as the ball is in contact with this sphere at this point, so normal force would act in this direction, so away from the contact direction. So the normal to the surface, contact force, that is normal force, would act normal to the surface. So for this surface, so here the surface is horizontal, so in this direction contact for normal force would be acting. Here this is a sphere. For sphere, radius is the normal. So here if we draw tangent at this point, so normal to this tangent is radial in direction. So here also in radial direction, that is in this direction, the normal force would act in radial direction. So this is the direction of normal force, and here gravitational force vertically downwards. And here what we need to find out is height of the particle from this center of mass point. So this is the reference point we have taken, because this half of the circle would face gravity. So here this is the height we need to find out. At this point, the height of the particle from the reference point is this, so we need to find out this one. So if we draw here a parallel line, so from cos theta, so actually we need to find this. So let this be O, let this be B point, and let this be A point. So cos theta is nothing but adjacent side by hypotenuse, so OB by OA. So OA is nothing but radius of the sphere, so r cos theta is equals to OB. So OB is nothing but r cos theta. So height of the particle at this point is r cos theta. So hence we are having mgh in the place of h, r cos theta. So at this point, the height of the particle from this reference point, that is here from the center of the circle, this is the reference point. So that is r cos theta, and plus in addition to that, it would be having kinetic energy also. Here it is in rest position, So it would be moving, so it would be having kinetic energy also, and it is having rotational kinetic energy because it is rotating about the sphere. So this is nothing but rotational motion. So the particle is in contact with the sphere, it is moving like this in circular form, so it is in kind of rotational motion, hence it would be having rotational kinetic energy. And half mv square, v is nothing but r omega. From the well-known formula, v is nothing but r omega. So rotational kinetic energy, this is nothing but rotational kinetic energy, and omega is nothing but theta dot, that is d theta by dt. So how much frequently the angle is changing. So change in angle with respect to time, that decide, and that is angular velocity. So v is nothing but r omega. So r theta dot half mv square, in the place of v we are having r omega, r theta dot. So r square theta dot square. So from the law of conservation of energy, we would have this equation. From this equation, here m, here m, here m would get cancelled. And if we send this cos theta to this side, so here also gr, here also gr. So gr would be taken common, and here 1, and this cos theta would go to that side, that is gr cos theta would go to that side, that is nothing but minus gr cos theta. So gr would be common from this term. So half r square theta dot square. So this is one of the equations. And another thing is, here this is the direction of mg. So gravitational force would act vertically downwards. So here this angle is theta, and this angle also would be theta. So we can split this into two components. So this is mg cos theta, and so here it is like mg, this would be angle theta. So this mg can be splitted up into mg cos theta and mg sin theta in this direction. So here we would be having mg cos theta, and in this direction mg sin theta which would be balanced with this opposite frictional force. So this this force would get balanced by this frictional force. And here if we take this particular part, that is forces acting along vertical direction, so here we would be having mg cos theta in this direction, and in the upper direction normal force, as well as the particle is moving, so it is in rotational motion, and it is moving, it is a kind of central force, it is moving about this center. So as it is moving about this center, it would have centripetal force, so which acts outwards. So what we would be having is from this, so here mg cos theta in this direction, so this is mg and this is mg cos theta, so mg cos theta, and in opposite directions, that is here radially outwards, we are having normal force, as well as and centripetal force, that is nothing but m or mv square by r, or m or omega square. If we put v is equals to r omega, then we would have m r omega square. So here m r theta dot square. So we would be having another equation of this form. So if we send this n that side, we would have mg cos theta minus n is equals to m or theta dot square. So hence we are having mg cos theta minus n is equals to m or theta dot square from the balancing of those forces here in this direction. So here mg cos theta in this direction radially inwards, and n normal force radially outwards, and centripetal force m r theta dot square. So this is the another equation. So when the particle finally loses contact with the sphere, so these are the two equations we are having. And when the particle loses contact with the sphere, so what I have said, normal force is a contact force. It acts only when the two bodies are in contact. Here this particle has to be in contact with this sphere, only then normal force will act. So when it loses contact with the sphere, then will not be any normal force, because it is a kind of contact force. So when it is not in contact, normal force becomes zero. So we would have mg cos theta 0 is equals to m or theta dot square here from this equation. So mg cos theta is equals to m or theta dot square, and r theta dot square could be found from this equation. So here we are having one r, two r's, that is r square. So one r and this r would get cancelled. So this 2 would go to that side. So 2g into 1 minus cos theta is nothing but r theta dot square. So in the place of r theta dot square in this equation, we would have g into 1 minus cos theta, g into 1 minus cos theta, and that is 2g into 1 minus cos theta, sorry here. So in the place of r theta dot square, r would get cancelled. So 2g into 1 minus cos theta is nothing but r theta dot square. So here in the place of r theta dot square in this equation. So m would be as usual, or in the place of r theta dot square 2g 1 minus cos theta, and n would become 0. So finally we would have this equation. So in this equation we can cancel this mg over here. So finally what we would get is cos theta is equals to 2 into 1 minus cos theta. So this is nothing but cos theta is equals to 2 minus 2 cos theta. So this minus 2 cos theta would go to that side and it would become plus 2 cos theta. So cos theta plus 2 cos theta is nothing but 3 cos theta. So 3 cos theta is nothing but 2, and cos theta is nothing but 2 by 3. By solving this equation, finally we would have cos theta is equals to 2 by 3, and theta is nothing but cos inverse of 2 by 3. So this is a required answer. So what they asked us to find the angle at which the particle leaves the contact with the sphere. So as we assume this is the angle, and finally we have found the angle in terms of cosine terms, that is cos inverse of 2 by 3. So at this angle, this particle would leave this sphere, it would lose contact. So this is the problem and its solution. So thank you.